Good afternoon, my name is Sara Garzon and today I'm going to present my PhD thesis that I developed at University Carlos III of Madrid and whose title is Connecting 3D Printing Parameters and Mechanical Properties of Fused Deposition Polymers, Experiments and Modeling. So in this presentation, first I would like to introduce the motivation and the objectives of the research that I developed. Then I would like to present the three parts that my PhD thesis is split in. The first one is an experimental characterization of this fused deposition model in thermoplastic. Then I will present different tools that we propose to capture and simulate the additive manufacturing process and the constitutive model that we develop for these new materials. I would like to summarize the main conclusions of this research, and finally I will present the achievement owed to PhD. So, traditional manufacturing process uses to manufacture polymeric components such as extrusion or injection molding have great limitations when we want to manufacture components with specific and complex geometries. In the 80s, the first 3D printing was created, and since then, additive manufacturing technologies have been growing. Among the different advantages of additive manufacturing, we can find an efficient use of material, we can manufacture lighter components, what is so important in different industries, shorter production times, and great flexibility in the design. So, because of all these advantages, additive manufacturing are currently employed in different industries, such as aerospace industry or, for example, automotive industry. However, these technologies are only used right now to manufacture simple components. So, the question that we ask ourselves is, why have this technology not completely replaced the old-fashioned manufacturing process? Why additive manufacturing is not used to manufacture complex components such as an aircraft engine? So the first thing that we did is try to manufacture different specimens using additive manufacturing, and we developed different experimental tests, like impact tests or characterization under the Hopkinson bar, and we found that the behavior of these new materials is much worse than the same that these materials present when we use traditional manufacturing process. In addition, we couldn't be able to find why this the new defect that we observed in these ones were produced. So the first thing that we did is that we went to the literature and we analyzed the characteristic of a specific additive manufacturing technology that is one of the most famous, that is fused deposition modeling. And we found that these components present an anisotropic behavior due to the direction of 3D printing, additional porosity due to the manufacturing by layers, and also that the mechanical properties of these components are influenced by the printing parameters. That means that depending on the printing parameters that we choose as a user, the mechanical properties are going to change. However, far from considering the porosity and the anisotropies at a disadvantage, what we thought is that we can use that ones to produce customized mechanical properties. The only thing is that we need to be able to control the influence of the printing parameters. So the objective of my PhD was to optimize the printing parameters to find the optimal mechanical properties. That means that we wanted to propose different tools to be able to optimize these printing parameters and to find the optimal mechanical properties. And to find this link between the printing parameters and mechanical properties, we developed a methodology with three different parts. As I said, the objective was to develop different tools to help us in the optimization. But first of all, we carry out an experimental characterization in which we analyze the influence of the most relevant printing parameters. Then we propose different tools to reproduce the 3D printing process and to understand this one. And finally, with all the observations, we propose a new constitutive model. I would like to also say that this link between printing parameters and mechanical properties was done having into account that these materials can present large deformation, strain rate dependencies. We also analyze the failure of these new materials, the anisotropy due to the 3D printing process, and also the viscoplasticity that these materials present. Now, I would like to go to the first part of my thesis, that it was the experimental characterization. As I said, the objective of this one was to analyze the influence of different printing parameters on the mechanical properties. And for that, well, the first thing that we did is manufacture different specimens using different combination of printing parameters. And we studied the influence of 3 of them, that it was the layer height. We used 3 different layer heights, 2 raster orientation, and different combination of the number of layers. Once that we manufacture the specimen, we analyze the mesostructure of these new materials under a scanning microscope, electron microscope. Then we carry out different tensile tests at different strain rate, and finally we analyze the failure of these materials during and after testing. So the objective of this first part was that, analyzing the mesostructure, we observed that fused deposition modeling the mesostructure of fused deposition modeling components is highly influenced by the layer height, and we observed that the void density increased as the layer height increased. Then we carry out different tensile tests. As I said, we use 18 different combination of printing parameter sets. We test this specimen at 2 strain rates, resulting in a total of 140 tests. So, analyzing the mechanical behavior of these materials, we observed that the mechanical properties improve when the layer height and the number of layers decrease, and also that the behavior is completely different if we compare longitudinal raster orientation with a transversal one. That's not only in the stress strain response, but also in the failure. While longitudinal specimens present a ductile failure, the transversal ones present a brittle one. Now I will continue with the second part of my research. So the objective of this computational modeling was to develop different tools to reproduce the 3D printing process of fused deposition modeling components to help up in the optimization of the printing parameters. As we saw before, the printing parameters has an influence on the mesostructure. And we wanted to know what does happen. So the first thing that we did for that, it was propose a thermal model. And we proposed this thermal model because the temperature history of the filaments during the 3D printing has a great influence in the final quality of the bond that is achieved between filaments that are adjacent. The second thing that we did is propose a sintering modeling. The sintering is defining as the coalescence of particles under the action of the surface tension, and this model allows us to reproduce the bonding process that takes place between 2 adjacent filaments during the 3D printing. So we combine with fully coupling these 2 models in the sense that the temperature that the thermal model gives us allow us to update the value of the viscosity and the surface tension for the sintering model, and at the same time, the bonding between filaments is going to have an influence in the thermal evolution. So once that we have these 2 models coupling, we propose some analytical expressions to predict the void density and also the mechanical properties. With all these tools, we combine them to predict the mechanical properties, and we compare that predictions with the experimental data from that we got in the first part. So as a conclusion of this second part, We combine a thermal and sintering models into a two-stage model to simulate the bonding process during 3D printing. We propose some analytical expressions for the prediction of the void densities and the mechanical properties, and we use all of them to carry out a parametric study in which we analyze the influence of different printing parameters such as the layer height, the printing speed, the environmental temperature, and the platform temperature. And I would like to say that from this analysis, we observed that the layer height, it was the printing parameters with highest influence in both in the void density and the mechanical properties. Now, I would like to continue with the third and last part of my research. The objective of this last part was to develop a hyperelastic constitutive model for fused deposition modeling components. And in this model, we include the anisotropy due to the 3D printing, the strain rate dependency, and also other dependencies due to the printing parameters. So the first thing that we did is we developed the formulation of this model in which we have into account that these materials present an elastic response, also a viscous response, and in the case also of longitudinal specimens, we observe a viscous plastic response. And I would like also to say that to do that, we went from the reference to the current configuration using two extra intermediate configurations. Once that we have the formulation, we identify the model parameters for a specific material, that is the AVAs, that is one of the most used in 3D printing, especially for fused deposition modeling. And finally, we validate this model comparing the predictions with the experimental results. As a conclusion of this last part, I would like to say that we propose a new constitutive model for fused deposition modeling materials with infinite infinite deformations. That we the constitutive relations of this model are derived from energy potentials within a thermodynamic consistent framework, and that we have into account different dependencies such as the strain rate, the anisotropy due to the additive manufacturing process. Here we have the A, that is the direction of this where the components are manufacturing, the porosity due to that at the same time the porosity is influenced by the layer height and other printing parameters, and also the number of layers dependency. And I would like to say that is the first model that we found in the literature with all these dependencies, considering all these dependencies. The model showed good capability to predict all the dependencies on the different variables that I have said. As for example, here we can see the different predictions that we did. So now I would like to summarize the conclusions of all this, all the research. I would like to say that the thesis developed a complete study going from the experimental characterization, but also with the development of different computational tools that allow us to understand the 3D printing process and to predict the mechanical behavior depending on the 3D printing parameters. And finally, we propose a constitutive model for these new materials. This research allowed to deepen the understanding of the influence of printing parameters on the mechanical properties of fused deposition modeling thermoplastic. Then I would like to say that during my PhD, I published a publication, and I would like to highlight one of them that I had received 42 citations in a year. An achievement on to the PhD, I would like to say that this thesis was awarded to the UC3M Standing Award for the best thesis in mechanical engineering. That after my PhD, I got a contract as a postdoctoral research at University in Oxford, and in this project, I currently using the knowledge that I learned during my PhD, and I'm using all the things that I know about additive manufacturing to try to optimize different components also manufactured by additive manufacturing, but with more industrial applications. The methodology that I developed during my research is currently employed in the project biomechanical simulation, stimulation based on 4D printed magneto-active polymer, in which the PI is one of my thesis director. To conclude, I would like to say thank you to my PhD director, Dr. Daniel García González and Professor Ángel Aria. Say thank you to the Dynamic and Fracture of Structural Elements group from UC3M, Professor Antoine Jerusalem, who was my supervisor during my research stage as a visiting student at University of Oxford during my PhD, and all the international collaborators I have worked during the development of this PhD thesis. Thank you very much for your attention.